All right, today, what we're going to do is we're going to look at Chapter 1, Section 2. Now, this is the second part to Chapter 1, Section 2. This will finish it up for it, and we should be getting ready to take a nice quiz/test for this stuff on Friday. So that's the goal, is to get everything done by Thursday, so that way we can have a test on Friday, or maybe get prepped for a lab on Monday. So we're going to be looking at classifying matter. What you need to have an understanding of before you're finished with this is, how can you classify examples that are given to you? How can you classify that matter? Is it classified as an element, pure substance, compound, colloid, solution, all those good things. So you've got to be able to do that. Explain why carbon and copper are classified as elements, not compounds. What an explanation would be between the difference between elements and compounds. Some of this stuff should sound familiar to you, but let's take, for example, everybody knows what an element is. You go to the periodic table of elements, you got your examples. But do you know what a monatomic atom is? What diatomic is? So we will get into some more details, but you just have to get through the basics first, or for me to know what your background is. All right, and then the last thing that you got to be able to understand from this is to be able to describe differences between what pure substances are, those elements and compounds, why are they pure substances, and then what are mixtures, so what the difference between those are. So if in your notes, and I'm talking outlines, not the notes that you have up on the screens right now, if you struggle through any of the notes, you're not sure what's going on, maybe you forgot what a term is, or you're having troubles remembering something, then I would suggest you write something like this down right here, this chart, on your outlines. You have the space that's to the left of your outlines. That's for any extra notes that you want to put. And remember, for this test that's coming up, I'm letting you write anything down on those outlines, and you can use only those outlines on that test. All right? So when we start classifying matter, we cannot classify things strictly on whether they are solids, liquids, or gases, because that's just too generic of a description. It'd be like me trying to get an understanding of what type of car I drive, and I tell you it has 4 wheels. Well, there's a whole bunch of cars that drive on 4 wheels. So that's too broad of a topic. All right, and what we'd like to do is be a little more specific when we're trying to describe the makeup of matter, okay? And instead of describing it as states of matter, solid, liquid, gas, we could, if we're looking at states of matter, you can throw in there plasma, and then the 5th state of matter that no one really goes over and talks with you guys about is that Bose-Einstein condensate that occurs just a few nanodegrees above absolute zero. No one really ever talks about that. But anyways, getting back to classification. Instead of describing it based on state of matter, we're going to describe it as elements, compounds, mixtures, solutions. So to begin that, we're going to use these 2 terms right here. We have homogeneous and heterogeneous. This should be an easy thing for you to remember, because you've used hetero and homo before in terms of sexuality. If you have heterosexual, you're talking about 2 different sexes. If you have homosexual, you have the same. Well, if we use the prefix hetero as different, then right here we can look at a couple of examples of matter that is heterogeneous in nature. So what makes these heterogeneous in nature? Well, in the pizza example, you've got olives, you got green peppers, you got cheese, you have sauce. All of those things retain their individual properties when they're mixed together. They can be in any varying size or quantities. They're just mixed together. All right. Now, if you don't like the olives on there because they retain their individual properties, they can be removed easily. For the snow globe here, it's made of different things, heterogeneous in nature, and because the little paper that's inside of there, its properties are different than the water, then we can separate it with an easy method also, just using some filter paper. Our last example over here, we have a piece of granite. Now, this granite rock, you've got some what's called some orthoclased feldspar or plagioclased feldspar. The orange is a plagioclased feldspar. It's a type of mineral. Then you go to quartzes and micas that make it up. So if this is a mixture right here of those different minerals, we can separate it. Now, it's not going to be as easy as, say, pulling off the olives, but it's not terribly difficult either. What we have to do is we have to heat this up to the different melting points. So our feldspars and the micas and the quartzes, they all have different melting points. They all retained their individual properties, that physical property, the melting points, and based on that, we're able to separate them out fairly easily, okay? So those heterogeneous mixtures, each one of those had two or more things that were mixed together, but the key here is that when these things are mixed together, you have to understand that they are not being chemically combined, all right? So two or more things, the cheese, the green peppers, the olives, the water and the pieces of paper, you've got the quartzes, feldspars, and micas, all that stuff was together, but not chemically bonding with each other. All right, so they all kept their separate or homogeneous identities. All right, so each one kept their individual properties. Now, it's not to say when you mix things together that it's always, all of the substances are going to keep their exact properties, because when you mix some things together, you might get some dissolving. All right, so you put sugar in the water, let's say. Now, that's not a heterogeneous, but I'm just using this as an example. If you mix sugar in the water, the sugar dissolves, but it's not been chemically combined because you can still taste sugar. All right, if you have water that boils, well, the temperature's risen. You might have cheese that melts. You might get a color change that appears, but it's still the same material. Now, the other example I have here of a heterogeneous mixture is if you have salt and pepper. So if you take a second, you think, all right, we have two different materials, two specific individual properties each. How can we separate those two mixtures? All right, you got to think about, what does salt do that pepper doesn't? Well, if you put salt and pepper together, somebody might say, well, I'm going to take the individual pepper grains and separate them out. Well, that's going to be a very tedious task. It's going to take forever to do. So a smarter choice might be to take and throw it in the water. The salt will dissolve, the pepper will float, you can skim the pepper off. Because each of those materials retained their homogeneous natures, their homogeneous properties. Salt, when put into water, it dissolves. Pepper, when it is put into water, it floats. So pepper's density is less than that of water. Salt, the sodium and the chlorine, they disassociate or separate when they're put into water. So each of those, based on their different physical properties, they were able to easily be separated. Now, some other examples of methods of separating, we already mentioned one of them a little bit earlier. We had the snow globe. The snow globe, if you wanted to separate it, you use filtration, different particle sizes. If you want to separate two materials and one of them is magnetic, like iron and sulfur, you can use a magnet for that. Chromatography, if you want to separate inks based on the different makeups of them, the different densities of those inks, you can do that. An example of this, and I always kind of joke around that M&M, the manufacturers, they made such a big deal out of the fact that they were going to make blue M&Ms. But they always had blue ink or blue dye within the M&Ms all along, because brown, in order to make brown, you have to have blue dyes. So you can try this at home. You take a brown M&M, you get a little bit of water on it, and you rub that M&M across a piece of like coffee filter paper. So you have your filter paper and you've got a streak of that chocolate coating right here, that brown chocolate coating. Then you dip that coffee filter paper in some water, and through capillary action, the fibers are actually going to, that's not good. So what's going to happen is through the capillary action of the paper, that's going to draw the liquid up the coffee filter paper. And as it moves upwards, it's going to take the lighter dyes with it first, and the colors are going to start separating. So you'll see some yellows, some reds, some blues. So the blue M&Ms were always there. They were just kind of hidden. All right, we're moving on. If you have distillation, you want to get rid of the materials. Let's say you want to get rid of, I don't know, a liquid. If you want to get rid of a liquid and you know the boiling point, you can use distillation to remove the liquid. Crystallization, you're forming solids in a liquid. All right, let's go to the next thing. Our heterogeneous mixtures, they're going to be grouped up into two subcategories. We have the first one, colloids, and then the second one is suspensions. So every single day you consume different colloids and suspensions. You use different colloids and suspensions each and every day. So we'll take a peek at what some of those would actually be. All right. Now, if you don't get those terms, they're going to be coming up here anyways, so don't be worried. We got our first subcategory. You have colloids. Now, a colloid is heterogeneous in nature. It's made up of two or more different things. But colloids, the particles in them, they're very small, between 1 and 1,000 nanometers. Now, to put this into perspective, between 1 and 1,000 nanometers, you can't see them. All right. An example of a colloid is glue. You throw some Elmer's glue on the table. Can you see the individual particles that make it up? No. You pour yourself a glass of milk. If you look in that glass of milk, are you able to see the individual particles? Hopefully not, because if you do, you got some curdled milk or something. So, no, you can't see these particles. They're so small that they cannot be filtered out. They're too small to be filtered out. They'll pass. You pour milk through a piece of coffee filter paper, it's going to go right on through. All right. Now, a real easy way to identify if you're looking at colloids, not many people are going to pour milk through filter paper to see it, or try to look at it and tell if you've got particles you can see or not. Here's an easy way. If you have a solution, if you don't have to shake it up, and it appears to be murky, like your milk, if it is a stable and uniform mixture, you do not have to shake it up. The particles are all evenly distributed throughout the medium, then you more than likely have a colloid, okay? So, if we shake it up, or if we don't shake it up, if you do not shake it up, you might have a colloid, but just to double check, to see if you have a colloid or not, you can use a laser pen. Now, they do this in movies all the time. You got a bank robber going in, and they sprinkle some dust into a room, and then all of a sudden, the lasers for the alarms show up. Well, that smoke that they fill the room with, the dust that they fill the room with, the particles, they're too small to be seen, but they are large enough to scatter light. So in a colloid, that 1 to 1,000, well, that doesn't show up that well, 1 to 1,000 nanometers, you're not going to see those, but they are large enough that light can actually scatter off of them. So in the example over here, we have no light that's visible in this glass. The particles that might be making up this glass, now you know as well as I do that when you get a glass of water, you don't have just straight H2O, you have other dissolved minerals inside of there. So this tap water has got stuff in it, but the particles are smaller than 1 nanometer. They're so small that they don't scatter light. But in the colloid right here, because we can see the laser light being scattered, that means that you have distinctly a colloid. No particles have settled out. The light's big enough to, or I'm sorry, the particles are big enough for the light to scatter off of. You know that you're looking at a colloid. Now that's called the Tyndall effect, and it sounds like maybe one of your other science teachers had mentioned that. I asked a class yesterday, and they seemed to be aware of it. So this should just be a recall then. All right, just another picture. If you're looking at our different types of mixtures, you got solutions. Notice here there's no light that's scattering. Colloids, our particles are large enough that light starts to scatter. And then lastly, we have our suspensions that we're going to talk about in a second, that light does scatter or is completely blocked altogether. So what's the difference between a suspension and a colloid? Well, here you're looking at particles that are big enough for you to start seeing. So if you look at a suspension, you have particles that are larger, well, if it'll work, larger than 1,000 nanometers. So if something's larger than 1,000 nanometers, unless you have my poor eyesight, you're going to start being able to see them. All right, now, because they're so large, those particles can be filtered out, and they're large enough that your solution, that or the medium that it's in, there's not enough kinetic energy in that medium to keep the particles suspended indefinitely. So because there's not enough kinetic energy to keep them suspended, what's going to happen is they're going to start settling out over time. So anything that you have to start shaking up before you use, Italian salad dressing, fresh squeezed orange juice, and I'm talking about the kind with the nasty pulp in it, all right? No one likes, if you like that, you're just kind of strange. So the next type of example would be like house paint or mud. All of those, if you want to get the particles resuspended, you have to shake them up, all right? So we'll move on. We have just a little bit of time left. We've already mentioned those. So shaving cream, this would be a good example. Think about what shaving cream would be. Is that a suspension or is that a colloid? When you're looking at the different types of shaving cream, I'm talking about this one in particular right here. So there's no need to shake the can up. You press the trigger, the foam comes out. It is a stable mixture. It does not settle out over time. So this would be an example of a colloid right here. All right, we're going to go to our last type of mixture, and this is called a homogeneous mixture. Homogeneous, this key word has to be understood. Appears to be the same throughout. It is not the same throughout. You cannot say that it is the same throughout, because with a homogeneous mixture, like a solution, those particles, they're just small enough and so evenly distributed that it looks the same. They're so well mixed together. Now, because the particles are less than 1 nanometer, you're not going to be able to filter these things out. Now, solutions are what we're talking about here. Homogeneous mixtures, a solution. A lot of people want to group solutions just into liquids, all right? But it's not just that. The air you're breathing in right now, has carbon dioxide. You have H2O, you have nitrogen gas, you have all kinds of different gases that are in the room. So you cannot see the different ones. If you go to the back of the classroom, you're not going to get more oxygen than a person sitting in the front of the room. It's evenly distributed. Stainless steel is another example of a type of homogeneous solution. It's a mixture of different metals put together to make a more weather or corrosion resistant building material or a material to make different outdoor items for. So refrigerators oftentimes are made of stainless steel. Barbecues are made of stainless steel. And an interesting thing to save you some money, how do you know if you have a good stainless steel appliance that you're buying? Well, you take a magnet with you. If it's a good quality, high-grade stainless steel, when you put a magnet on it, it is not going to stick. It's just going to fall right off. If you take a magnet and you put it on a stainless steel barbecue, let's say, and it sticks, don't buy it, because that lower grade stainless steel is just going to rust out on you. All right. So our solutions, like I said, solutions, the particles of them, they cannot be seen. Why is that? Well, again, when we're looking at particle sizes, they're less than 1 nanometer. Really tiny. You can't see them. Okay. Second thing that identifies a solution is they cannot be separated by easy physical means. No tweezers pulling the particles apart. There's no form of filtration that's going to be working for that. So an example of what I'm talking about is if you have a glass of water and you put some salt into it, NaCl. When you put that salt into the water, the sodium is going to disassociate, separate from the chlorine like this, all right? But you're not going to be able to filter out the sodium. You're not going to be able to filter out the chlorine. If you did, it'd be a bad situation because sodium, in its raw form, reacts with water and you'd get an explosion. Chlorine gas is a deadly material. If you inhale that, it would be very bad for you. So when we have dissociation, those particles are just going to evenly be distributed throughout the solution. We'll talk more about why sodium and chlorine disassociates in water a little bit later, okay? But with those, I just want to say one more time, when you're forming solutions, they're not always going to be liquids. You have different metals that can be mixed together to get different properties. You have different non-metals that could be mixed together to get different properties. So just a couple of examples real quick. No one wants a 24-karat gold ring. If you had a 24-karat gold ring that's pure gold is soft. They used to say that miners would bite it, and if it left an impression into the nugget that it was gold, but if they bit it and no indentation was left, then they had pyrite or fool's gold. So the gold that you guys would get would be like an 18-karat or a 14-karat or a 10-karat gold ring. You get different mixtures of metals with gold to make them more weather resistant, to make them more erosion resistant. What we're going to do in here is we're going to make brass pennies. To make brass, you take copper, so we're going to use a copper penny, and we're going to plate it with zinc and then heat the thing up. Now, when you heat the copper up, the zinc is going to start to mix with the atoms of copper, and what we form is brass. Brass is a more weather-resistant material, a more corrosion-resistant material. So that mixture, that solution, we're talking about two metals put together to make something new. All right, something that would be more resistant. So what do we have to have in order to form a solution? You have to have two things. You have to have a solute. Now the solute is the thing that's going to be dissolved. It's the sugar that you're putting into your tea. It's the salt that you're putting in the water. If something can be dissolved, we say that it is soluble. Okay? So if it is soluble, then it can be dissolved. If it's not soluble, okay, oil mixed in with water. Oil does not mix with water, so it would be insoluble. Okay? Now the thing that's going to be doing the dissolving is called the solvent. The solvent is going to be the dissolver. Now, the solvent, the most common, what we oftentimes refer to as the universal solvent, is water. Now, why is water considered to be the universal solvent? This is why. Okay, so you have water. Water is H2O. So here we have an oxygen. Here we have a hydrogen. Now we haven't gotten to this in detail by no stretch, have we? But oxygen, by itself, it's missing 2 electrons. It needs to gain 2 more electrons. So I'm going to put here, needs 2 electrons. Hydrogen, it has 1 electron. It needs 1 more electron for it to be chemically stable. All right, so each of those need 1 electron. So how does water form? Water, an oxygen molecule, has a certain amount of attraction to it. So you can think of it this way. Oxygen is like a real popular person. Hydrogen is not as popular, okay? So the electrons are the friends that they're trying to gain. Oxygen is the more attractive of the two. It has a stronger pull. It's got a better personality to it. So the electron right here with hydrogen, because oxygen is a more attractive material, oxygen starts out with 6 electrons like this. So we have 2, 4, 5, and 1, 2, 3, 4, 5, 6. All right, so we have 6 electrons and it needs to get 2 more to have 8. All right. Hydrogen has 1 electron, okay? So what's going to happen here is this electron, it's going to be attracted towards the oxygen, but hydrogen isn't just the ugly one. Hydrogen, it has some attractiveness, so it pulls the electron towards it. But because there's this tug-of-war contest between these 2 atoms, the hydrogen and the oxygen, because oxygen is the more attractive of the 2, the electrons spend more time closer to this. All right, same thing happens on this side over here. You have this electron, if it'll work, this electron is going to spend more time closer to the oxygen atom like this. Oh, it's getting kind of messy. All right, so if we count these up, our 2 electrons right here, these guys form a shared pair in between hydrogen and oxygen. These 2 share a pair of electrons between hydrogen and oxygen, and I miscounted. I need to put 2 more electrons up here. Okay, so no, I was okay because I have, let me count them out. I don't want to make a mistake here. We have 1, 2, 3, we had 4, 5, and 6. So no, I'm good. I'm good. All right, so you have your electrons that are distributed unequally between these 2 atoms, or these 3 atoms. Now, because the electrons are spending more time closer to the oxygen side, that makes the oxygen side more negatively charged. The hydrogen side of your molecule, because the electrons are spending less time near it, it makes it more positively charged. So, what else do you know of that has a negative and a positive side to it? A magnet. So your magnet, if we have a magnet, it has also a negative side to it, and it has a positive side to it. So we say that this magnet would attract other like materials. It would attract other magnets near it. So if we brought a second magnet near this, okay, so I'm going to put my little plus and minus on here. So here is my plus. Oh, that is the ugliest plus sign in the world. Okay, and you have your minus right here. What's going to happen is when you get two like materials near each other, so if this is a solution, okay, what's going to happen is, zoink, your two magnets are going to be attracted to each other. The positives are attracted to the negatives. So we're going to use this idea right here of two magnets, and we're going to relate it to our solutions. So water is the universal solvent. It dissolves a lot of different things because it is a polar molecule. Now that polar molecule, just like magnets, you got a positive side, you have a negative side. If we put another material in it, that's also polar. So if we have salt, NaCl, sodium, what it does is it gives its electron away to chlorine, and it makes the sodium more positively charged because it's given away its electron. Chlorine, it's picked up the electron, so it becomes more positively charged. So, water is a polar material, just like a magnet. Magnets attract opposites. So the positive attracted the negative attracted the positive. You have a positive sodium. Now that sodium, when you put it in the water, it disassociates, it separates away from. So if you think of associates like a law firm, they are together, but if they separate, they disassociate from each other. So this sodium atom, put it in the water, right over here. It's attracted to that side of your water molecule. And the chlorine, it gets attracted to, you guessed it, the negative side of your water molecule. Now there's a whole bunch more that's happening here. You have more than just one water molecule and one sodium chloride. You have a whole lot of them. So we could continue this where we have a whole bunch of water molecules surrounding your sodium, and the hydrogen are surrounding the chlorine. So, but I hope you get the idea that we form a solution. The solute, the thing that's being dissolved, you have the NaCl. This is your solute. And then the stuff that's doing the dissolving is the water. It's the solvent. Okay? Now I said that likes dissolve likes. Here you have a positive and a negative. That's the first one. You have a positive and a negative. That's the second one. So likes dissolve likes. And if we get into the last thing, if you've got, let's say, oil and water, you know that they don't mix, okay? Because oil would be a non-polar substance, and water is a polar substance. So because they are not alike, they're not going to mix well. They're going to be insoluble. All right, you're probably about done. We've got about 35 minutes into this. So if you still got a little extra time in class, I guess you can wrap it up. If not, we'll pick up from there tomorrow. Okay?